Okay. Now, in the first part, we've seen how standard neural networks will not be equivariant. And we've seen a few conceptually rather simple ways how to achieve equivariance in neural networks. And now we will make our way to exact built-in equivariance, which will be conceptually quite a bit more complicated. So for that, we first look at Cartesian tensors and the tensor product. So given two vectors V and W from the Euclidean space, the outer product will transform in the following way. Like this. So the outer product of two vectors in components, we can write it down like so. And then if we apply a rotation, what we will get will be the transformed coordinates. Every vector itself transforms with the rotation matrix R. So we will get something like this. RIK, RJL of TKL. And then this, we could say, is the representation that acts on this this tensor in components ij. Okay, and now here implicitly, maybe I should write this down, I use the Einstein sum convention. So that means that the indices k and l, which appear twice here, they are summed over. And we can show that this is again a representation. Okay, to do this, we just check the formal definition of a representation by applying two rotations to this tensor and then looking at this in components. So what we will get if we write this out is following contraction of indices. And then if we write this out once further, like this, here is the matrix product between these two rotation matrices. So we can write this out further by contracting over even some more indices and then reorder the matrices here. And then what we see is that this here, this is, if we compare against this expression here, this is exactly the application of the second rotation matrices onto this tensor and components, namely the components M and N here. And then this here in components is the application of the first rotation matrices onto this object here. And therefore, what we will get is that this is exactly the condition that we need to fulfill in order for this to be a representation. And this was now for two indices by taking the outer product of two vectors, and then every index basically individually transforms with a rotation matrix. And the notion of Cartesian tensors arises if we generalize this. Cartesian tensors, tensor representation would be that we take an object with just an arbitrary number of indices, where each index then transforms with a rotation matrix. So this will be the transformation behavior of Cartesian tensors, and this is a representation which acts on the d to the n-dimensional vector space. In our case, the Euclidean space. Okay, this is the Cartesian tensor representation. And then the second ingredient which we need is the tensor product. And this is a generalization of the outer product. Namely, if we have one tensor which has indices up to n, and then we have another which has indices up to m, then what we do in order to get a new tensor by the tensor product is just we take all of the combination of indices and then take all of the possible products. So this means that the object that will come out of this will have all of the indices of the input tensors, and the vector space in which this lives has the dimension of the product of the two vector spaces of these tensors. So if these two are Cartesian tensors, then this here will also be Cartesian tensor. There's one problem though, and that is that the dimensionality blows up. If we would use this as a mechanism in our neural network, it would be nice because it would be equivariant in principle. So if we know the representation of these inputs, we also know the representation of the output of this computation. But if we apply it iteratively and do a bunch of tensor products in every layer, then of course the dimension will be super large and this will not be feasible in practice. There's a solution, and that is we can decompose Cartesian tensors, decomposition. We can decompose them into irreducible representations, which are also called irreps for short. And in order to understand the notion of irreducible representations, we will look at another definition, namely the definition of subrepresentations. Subrepresentations. Okay, let W be a linear subspace of the vector space V, in which we have a representation defined, which is also G invariant. Okay, what does it mean for a subspace to be G invariant? It means that if we apply any group element, the action of any group element to an element from that subspace, that we will stay within the subspace. This should hold for every element subspace and for every group element. Then in this case, we say that the restriction of the representation onto the general linear group of just a subspace is a subrepresentation. So this is the formal definition of subrepresentation, and this is what we need in order to define when a representation is reducible, namely a representation is reducible if it has non-trivial subreps and non-trivial subreps are subreps other than restrictions to the full vector space or just the null space. And else it is said to be irreducible. Okay. We look at an example for reducible representation, namely this representation that we've looked at up there, the one with the outer product of two vectors. In components, this was the following transformation behavior, or if I write it as matrices, this would be the following. This is a reducible representation. How can we see this? The trace is a 1D linear G invariant subspace. Since, okay, how do we see this? We apply the trace to the transform tensor. And if we write this out, what we get by just copying from up there is the following. Now we can use cyclic permutations in the trace, which leave the trace invariant. So we get the following. And then this here is the identity matrix. So what we end up with is, again, the trace of the untransformed tensor. So this is the trivial representation. So we've seen that inside of this Cartesian tensor representation with two indices, we have basically a subrepresentation. That is, if we only look at the trace as a linear subspace of this d by d dimensional space, then we find that the group on this subspace will just act as with the trivial representation. So what we find is that this representation, if we look at the special case of 3x3 representation, so if we look at the three-dimensional Euclidean space and the rotations in there, then this decomposes into irreps in the following way. So if we write this in a notation which is based on a dimensionality, so if we say that this is 3 by 3-dimensional, so if I write something like an integer with this underbar here, it means dimension, then this decomposes like such. Okay, what does that mean? I take a, actually maybe, okay, to take a step back. Okay, we will see this in a second, why it's this decomposition. First, we start formally with a new chapter, decomposition of Cartesian tensors into irreps of SO3. Okay. And now we are specifically considering the case of three-dimensional rotations. And I'm going to introduce this dimension notation with a few simpler examples first. So we've seen that we have the trivial representation, which acts on just the one-dimensional Euclidean space, and then we would denote this with a 1 underbarred, and we've seen the vector representation on R3, and this let us denote with, according to the dimensionality, with 3 and then this underbar. And now these two representations, they are already irreducible. But this representation here, in the 3 by 3 dimensional case, it can be decomposed. And a part of it we've already seen, namely this one here. This one we've already encountered. This one is this linear subspace that corresponds to the trace. And then there are also, I'm going to write this down again. So we have this decomposition, Tij, this in terms of dimensions, it was correspond to 3 tensor product with 3, so outer product of 2 vectors, and then it decomposes into irreps with dimension 5, 3, and 1. So just to check this representation is 9-dimensional, 3 by 3, and then this representation is 5 plus 3 plus 1, also 9-dimensional. So already the dimensions check out. And then this here is a direct sum of irreps. Where this scalar part here, this invariant part, one-dimensional part, corresponds to the subspace corresponding to the trace. The 3-dimensional part is the antisymmetric part of the Tij, and the 5-dimensional part is the symmetric and traceless part. So these are the 3 irreducible representations which one gets. And then after this decomposition, how one can imagine how this direct sum representation will act on a 9-dimensional space will be by a block diagonal matrix, where up here we have 5 by 5 entries, here we have 3 by 3 entries, and then down here we have 1 by 1, and everywhere else we have zeros. Log diagonal. Okay. In general, yeah. So the question is, how does the representation of the direct sum work to represent this matrix here, which is 3 by 3? Okay, the way that this formally works is we first identify the subspaces, which are G invariant. And then what we want to find out is, how does this representation now act on these subspaces? And for the trace, we've seen it explicitly. It just acts with the trivial representation, where this here is actually just a 1. And then we need to do a change of basis onto our vector space to basically make elements of the vector space fit with this representation, such that always in the lowest entry of this 9 by 9 vector, basically if we flatten this, then in the lowest entry of the 9 by 9 vector, we have the trace of this matrix here, and then up here we have the antisymmetric part, and then here we would have the symmetric traces part. Yeah. Okay. So this is the decomposition of now the Tij with 2 indices. One can go one step further and look at the decomposition of Cartesian tensor with 3 indices in dimensions. This would be 3 by 3 by 3. And then we can use what we've already worked out here to write this as a direct sum of irreps. And then we can further write out this product here, like so. Into a direct sum of product representations, one could say, single products. And then these one can, again, these are irreps now, and they can again be decomposed into irreps. Yeah, by similar rules. This 3 by 3 decomposition we've already worked out. This is this here, but now one question would be, for example, how does one do this 3 by 5 decomposition? And yeah, there's a general rule to do this. The general rule is the following. Okay, before we go to the general rule, first I'm going to introduce one more notation about irreps. So irreps are labeled by degree L. And have dimension 2L plus 1. So you've seen that these dimensions of the irreps, they're always odd. In the cases we've seen so far, but they continue to be odd all the way. And this is why we just label them by L and get the dimension by 2L plus 1. And then let me write down the transformation behavior of such irreps. So tensors that transform under irreps. They are called spherical tensors. We will see in a bit where its name comes from. And the transformation behavior of them looks like this. So if we have a tensor which lives in the R to the 2L plus 1 dimensional space, so this will transform under the irreducible representation labeled by L, then the coordinates will transform like this. where we use the so-called Wigner D matrices, which are the representation, or which give us the representation from a rotation in 3×3 to a matrix that is 2L plus 1 times 2L plus 1 dimensional, and can then act on this tensor. And this is a bit odd here. The indices of these spherical tensors, they are enumerated not by 0, 1, 2, 3, and so on, but they are enumerated from -L to L. This will always give us 2 to the L plus 1 entries, and this is a convention which shows a connection to quantum mechanics, basically, which I will say a bit more about in a second. Okay, now the general rule, which I promised how to do the decomposition, at least in dimensions, is, in general, we have the following rule. This is why I needed to introduce this notation of the L. If we have an irreducible representation of degree L1, and we have an irreducible representation of degree L2, then if we take the tensor product between them, we will get something that is 2L plus 1 times 2L2 plus 1 dimensional. And we can decompose this into irreps again, into a direct sum of irreps like so, that we take the label L for the combination of the irreps, and this runs over the absolute value of the difference of the two up until the sum of the two. And these will be all the irreducible representations in terms of dimensions, which we will get out if we take two irreducible representations and do a tensor product between them. Okay, now how does this solve the problem that we had before? That basically if we take tensor products, the dimensionality will blow up. In principle, if we do this decomposition, we still have the same dimensionality as before, right? But if we do the Cartesian tensor product between Cartesian tensors, what we will get out is one large tensor representation, which we will have to keep as a block in order to maintain the equivariance in our neural network. But if we do the decomposition into irreducible representations, we get out a number of representations which are smaller by themselves, and out of which we could select only a subset to continue with them and ignore the rest. Or we could also combine them by adding them. If they have the same type, we could add them up and they would still have the same representation afterwards. And this is how we basically solve the problem of the dimensionality which blows up. If we take tensor products as core equivariant operation in our neural networks. Okay, but this was only in terms of the dimensions. Now I want to show you how this works, how this decomposition here works in terms of the coordinates. And what we need for this are the so-called Clebsch-Gordon coefficients. So if we have spherical tensors X, which transforms under the irreducible representation labeled by L1, and we have another spherical tensor with the representation L2, then how can we get out the coordinates of a representation labeled by capital L? So we get the components of this 2L plus one-dimensional tensor by the following rule. We sum over L1 over M1 and over M2, which are the coordinates of these spherical tensors here. And then the linear combination which we take is weighted by the so-called Clebsch-Gordon coefficients. So we take the following contraction. So this here would be the M1th component of the spherical tensor X, which lives in the 2L1 plus one-dimensional Euclidean space. Yeah, and this is the general rule. These Clebsch-Gordon coefficients, they are sparse. So we only get non-zero entries, or a non-zero contribution here. Non-zero only if two conditions are met, namely that the capital L lies between the sum and the absolute value of the difference of these dimensions, or of these L's of the input representations. And the second condition, which needs to be fulfilled, is that the capital M is the sum of these component labels M1 and M2. Okay, who here has encountered the Clebsch-Gordon coefficients before in their studies? In quantum mechanics, with decoupling of angular momentums, right? This is quite a deep connection, actually, that the irreducible representations of SO3 and the eigenstates of the angular momentum operator in quantum mechanics, that they basically both use the Clebsch-Gordon coefficients for the decomposition, and that the same mathematics basically arise here as in the coupling of spin states. For example, if you have two electrons in helium, then you get the coupling of the angular momentum eigenstates, and you can use the same coefficient, the same Clebsch-Gordon coefficients to go to the eigenbasis again of the angular momentum operator. And this is maybe just how I could also make plausible to you these rules here. Basically, what we have here is that the total angular momentum should fulfill this triangular equation, that either the momenta are completely anti-aligned or they are completely aligned. And this condition here would be that the z component of the angular momentum should add up. So this is how this is motivated, and how there is a connection to the same mathematics actually arising in quantum mechanics in coupling of angular momentum. All right, so far so good. We have now seen how to basically get spherical tensors by taking tensor products and then doing the decomposition into these irreducible representations. There is another way, though, how we can get spherical tensors, namely using the spherical harmonics. So the spherical harmonics, which maybe in this context of quantum mechanics and angular momentum, you know as the position space representation of the angular momentum eigenstates, they appear in many different topics. For example, they also form an orthonormal basis for functions on the sphere. But for our case, we will look at them, this spherical harmonics, which I denote by this, as equivariant functions, which map from the sphere to spherical tensors of degree L in the way that if we look at the transformation of such spherical harmonic functions by, for example, rotating the input by, which is a three-dimensional vector here, normalized to the sphere. If we rotate this by some rotation r, the transformation behavior will be exactly the one of spherical tensors, namely with the contraction using the Wigner D matrices from before. So this here would be an element in three-dimensional space, which indicates the direction by being normalized to sphere. Okay, now with this, we actually have all ingredients that we need to build. Yeah, we have all ingredients that we need to build equivariant layers, but do you have any questions at that point? Okay, so the thing that we will look at are equivariant point convolutions. And for that, let me define what a point cloud is. A point cloud is a set of nodes labeled by index I with features, node features Fi located at positions xi in Euclidean space, and yeah, and then a Euclidean graph would be a point cloud plus, so it's the same thing as a point cloud plus edges ij between nodes. And yeah, these are very common objects, as typically the inputs of geometric deep learning problems. So examples would be molecules or 3D scans from LiDAR scanners, particles in an n-body simulation, detections of particles in a particle collider, for example. So yeah, various different data modalities here. And the popular machine learning approach to tackle this are message passing neural networks, which combine information by sending messages between nodes and thereby updating the node features. So the node feature at a later layer, I'm now using T as an index to label the layers because L is already used for the irreps. This will be given by the direct sum over the neighbors with respect to these sets of edges here of the neighbors of the node I, and then some function. This is now an example. Different ways to construct message passing network. Some function H here, usually in MLP, for example, which takes in the features of the neighbors and also takes in the relative position vector. By the way, I already mentioned to you earlier that also translation is a symmetry which is of interest, and this is usually how translations are handled. One typically always only uses relative positions, so differences between input positions, so that the absolute placement of the origin of your coordinate system basically doesn't matter. So this gives you translation invariance. And then one special case of this would be SO3 equivariant convolutions, which uses everything that we've discussed so far about the tensor products and the spherical harmonics and builds an equivariant layout of this. So the way that this would work would be we take, again, we aggregate over the neighborhood of this node I, and we look at the features at the neighboring nodes at the layer T, and then we take a tensor product with a spherical harmonic of order L of the, let me define here this shorthand here, Rij for the relative distance vector. We normalize it to be on the sphere. And then we take this tensor product between spherical tensors. But this, so far, could be seen as basically the convolutional filter, the angular part of the convolutional filter. But we also want to take the radius, so the distance to our nearest neighbor, into account, which we do by another function which considers just the length of this distance. And then what are the other ingredients that we have? This aggregation here. So this is not the direct sum. This is a bit unfortunate that the two symbols are used the same here. This circled plus is, in the other case, it was the direct sum. And here it's an equivariant aggregation operator. So we aggregate the messages from the neighbors. To make this equivariant, it could, for example, be the sum or the mean, but not the component-wise max, for example. This would not be equivariant. And then this circled cross here, this is the tensor product plus the decomposition into irreps. Which is implicitly included here. Yeah. Yes. Yes. So the question was if I could provide some additional reading material. I will give you 2 references for the lecture for today. Then I will give the summary. So one will be references. Would be E3 and N, Euclidean neural networks. And the other one is called A Hitchhiker's Guide to Geometric GNNs for atomic systems. These are 2 papers which you can find on the web and which give a good introduction to the topic. I would have liked to tell you quite a bit more still. For example, open questions. Okay, now we have seen how to do point convolutions in an equivariant way. But I already told you before that standard linear layers are not equivariant, that standard nonlinearities like ReLU are not equivariant. Then there's also the problem, usually modern architectures use normalization layers, how to make them equivariant. There have been solutions for all of these problems, but I think today time is up. And so to summarize, we have learned today about how to make neural networks equivariant, which means to incorporate known symmetries that systems of interest have into the machine learning models, which usually just learn from data. So for me as a physicist, this is some good news that not all prior understanding of the system is just thrown aside and you let big data do the job. Yeah, in particular, the concept of equivariance is very relevant to machine learning in the natural sciences, where symmetries often play a crucial role and where you also have systems which exhibit exact symmetries. We've seen some part of the cool theory that is behind equivariance in neural networks. There are many different other approaches how to make neural networks equivariant, but essentially all of which I know are really based on the things that we've seen today, the decomposition into irreducible representations, the group theory background with representation theory. Yeah, so that's it from my side. I wish you a good rest of the week and see you next time. Thanks.